Hi guys, so today we're going to be looking at Chapter 10, Section 2, Independent and Dependent Events. So let's check out what an independent event is. An independent event occurs when one event does not affect the other one. So, for example, a student is taking a test or a quiz randomly and guesses on 4 of the answers. So let's say that you have a quiz here. You have 4 different questions and we're trying to state, is it a true statement or is it a false statement? Rather than really solving it ourselves, let's say that we just guessed on every single one. What I would say is an independent event is guessing the question 1 correct and question 2 correctly. Those would be independent events. Just because I guess this question correct does not mean that that's going to affect the second question that I answer. So in the case of an independent event, all we need to do is find the probability of the first event and multiply it with the probability of the second. And that's it. The other type of event that we're going to be looking at is a dependent event. And just like the word dependent, it occurs when one event does affect the other event. So they are dependent upon each other. So for example, a group of 4 students, including 1 boy and 3 girls, the teacher randomly selects one student to be a team leader, and he also picks another person to be the note taker. And these would be considered dependent events. The reason why is because during the first pick that the teacher does, the teacher is going to pick somebody to be the team leader, okay? And so now, in the options that the teacher is going to choose from, there's only going to be 3 students left because again, we already picked 1 student to be the team leader. And so this would become a dependent event because of the fact that our options went from 4 to 3. And so now we don't have just 4 choices, but instead we only have 3 choices to choose from. So based off of whatever our first choice is, our second choice is going to depend on it, basically. And so this would be the formula that we use for this type of situation. I'll go more in depth about how we use these formulas in the next few examples. Okay, so let's say, for example, we are asked to find the probability of the following. It says, as a part of a board game, you need to spin the spinner, which is divided into equal parts. So this is our spinner, and it's divided into 8 equal parts. Find the probability that you give a 5 on the first spin, and a number greater than 3 on your second spin. So just because I get a 5 on the first spin does not mean that that's going to affect my next spin. So this would be considered an independent event where, again, the first choosing does not affect the second one. So my outcome is always going to be that I have the option to get either 1, 2, 3, 4, 5, 6, 7, or 8. So my outcome is always going to be 8, whether it is the first spin or the second. So I'll make sure that both the first and second probability has the same outcome. They're still going to both be 8. Now, probability A is when we find the probability that we get a 5 on our first spin. So I'll write down that this one, what's the probability of getting a 5? And then the other one is finding the probability of getting a number greater than 3. So numbers greater than 3 would be considered 4, 5, 6, 7, and 8. So based off of that, I could say that I only have 1 chance out of 8 to get a 5. And then on the other one, I have 1, 2, 3, 4, 5 chances of getting one of those 5 numbers. So 5 out of 8. All I need to do now is just multiply those 2 together. So that was my first spin multiplying with my second spin. which equals to 5/64. And so my probability would be 5/64, or you can round it as the decimal point, 0.078. Okay. Okay, so let's try this one. It's asking us a bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, then randomly draw another bill from the bag. Find the probability that both events occur where event A starts off with drawing out a $100 bill, and then the second event is when we draw out another $100 bill. So if I were to think about this, I have my bag here, and from this bag we have 20 $1 bills, right? We also have a bunch of $100 bills as well in there. So if I were to take one from this bag, event A, I would have in total $20 bill, $1 bill options. I also have 5 $100 options. So for my first draw, I would have in total 25 options. I could get either the 20 $1 bills, or I can get a $100 bill, or 5 of those, one of those 5. Then after I take out a $100 bill, that means that in event B, I'm one $100 bill down. So in my little purse or bag here, I no longer have one of those $100 bills, so I only have 4 of them. Okay, and so because my options changed, where now I'm down $1 bill, that means that we have an independent event. So if I'm going to be looking at the probability of drawing a bill that's $100 bills in my first event, we would start off with 5/25, because again we have 5 $100 bills out of $25 bills in general overall. But from the second one, again, we no longer have 5, because again we took out one of those $100 bills from our bag, and so we're only left with 4. And on top of that, overall we only have $24 bills inside that bag. So I would write down that we have 4 out of the 24. Once I have my 2 events made, I just have to multiply them together. So I'm going to multiply 5/25 times 4/24, which would just be 1/5 times 1/6, and that equals to 1/30. And so that would be my probability, which would be about 0.033. Okay, let's try out cards. So you randomly select 3 cards from a standard deck of 52 playing cards. What is your probability that all 3 cards are hearts when, let's say for the first one, we're asked to replace each card before selecting the next card? So first few things to note is that we are looking at hearts specifically. And in a 52 card deck, we are given hearts, diamonds, clovers, and spades. And they're all evenly distributed in that 52 playing deck. So if you don't know how many cards we have that are hearts, all you need to do is divide 52 by 4, and we get 13. So we have 13 hearts in a 52 card deck, 13 diamonds, 13 clovers, and 13 spades. Okay. Now the important part of this sentence is that we replaced each card before selecting the next card. That word replacing is really important because of the fact that no matter what, let's say that I have like my cards here. If I take out one of these cards right? So I'm going to take out this card. I'm going to replace it with another card. So I'm going to take another card and replace it. Put that back in there. And then the second time, again, I'm going to be moving it out, and I'm going to get another card and replace it back into the set. So I will always have a full set of cards, no matter what. It doesn't change in numbers of outcomes. So because of that, again, tells us here that we are going to be selecting 3 different cards with replacements. So I'm going to have 3 different events happening. In the first one, again, we want to see if we get all 3 hearts. So we get 13 over the total number of cards, which is 52. And then, again, we replace the heart with another heart. So we still have 13 hearts. And we still have 52 cards. And again, it's being replaced. So we still have 13 hearts over 52. And so once I multiply all those together, that's just going to equal to 1 over 64. And that would be my final answer. Okay, so let's say that we do not replace each card before selecting the next. So that means that over here I have my card deck. All of my cards are here. And every single time that I take out a card, I don't replace the card. I just leave it on the outside. So the first time I take out a card, nothing to it. I don't replace it, I just leave it alone. And then the second time I take a card, I don't replace it, just leave it alone. And so you're going to see that my deck pile here is going to get smaller and smaller and smaller. There's going to be fewer and fewer options to how many times I will actually get a heart. So again, we are selecting 3 different cards. So I'll put down that we have 3 different events occurring. And then we're looking to see if we can get all 3 cards and what the probability of that would be if they were all hearts and they are not replaced. So again, in this case, we do not replace each card. So I'm going to start off with 13 hearts, and it's going to start off with the 52 overall. But then, again, I'm going to be taking away 1 card. So we get 12 over 51. And then again, I'm taking another card, 11 over 50. And so I took away a card, so I'm left with only 12 options out of the 52 of those cards. And then I take away another card, so I have only 11 hearts out of the 50 cards now. So it's slowly just taking away those cards. And so I'll be left with multiplying those 3, and that would give me 11 over 850. Okay, last one. So using a table to find the conditional probabilities. A quality control inspector checks for defective parts. The table shows the results of the inspector's work to find the probability that a defective part is passed, and the probability that a non-defective part failed. So they give us the table here. They say that it's defective but passed. There's only 3 of those, and there were only 36 defective that failed, and then there were 450 non-defective that passed, and 11 non-defective that failed. So if I'm trying to look for the probability that we have a defective part that passed, again, we're going to be focusing on this 3. But the main part that we need to understand how to find is going to be the bottom part, which is what is our outcome? What are we supposed to put here? We already know that we're specifically looking at defective parts that pass, so there's 3 of those. But specifically, we're looking at the pile that is defective. So I'll write here that we're only looking at all the defective parts. Defective parts. So the probability of that, again, all the defective parts are not only the ones that passed, but also the ones that failed. So I'm going to be adding 3 plus 36. And so that's going to equal to 1 over 13. For the next one, the probability of non-defective parts that fail. So again, non-defective parts that fail would be 11. So that part's easy. 11 is the easier part, but figuring out what is our general tile that we're looking at is the most important part. So if we're looking at the non-defective parts, which would be the 450 that passed and the 11 that failed. So underneath, I'm going to write down all non-defective parts, which would just be 11 over 450 plus 11, and that would equal to 11 over 461. Okay. All right, so hopefully this helped. Good luck.